Hi students, welcome to our physics channel, Physics and Me. I think most of you are watching my videos. I think that you understand the concept and you can do some numericals based on the concept as well. Now, I'm going to explain the continuation of the topic that is current electricity. Okay, in that I have done 3 videos. Once go through those 3 videos so that you can have an idea about what is meant by a charge and how does the charge move inside a conductor, okay, without connecting it to a battery, and after connecting it to a battery, how does the charge move. Charge means here it is electron, okay. So when that charge or when that electron moves with drift velocity, obviously we have discussed that when that electron moves with the drift velocity, then it constitutes the electric current. And I have explained what is drift velocity and what is a current. Okay, what is the relation between current and the drift velocity here? What is the relation between drift velocity and electric field here? And also, I have already explained about current density and drift velocity and the relation between the current density and the drift velocity. From that, we have derived Ohm's law. What is the actual form of Ohm's law we derived? That is, J is directly proportional to E. Current density is directly proportional to the electric field. From that, we are going to derive the actual Ohm's law, which we are discussing actually. Now, let us discuss about Ohm's law perfectly here in this video. I'm going to explain about Ohm's law and what is meant by resistance. How can we understand Ohm's law in a better way? Okay, and what is a difference between e.m.f and a battery? I mean, e.m.f and the potential difference, that I'm going to explain. Okay, so let us discuss Ohm's law first. What is Ohm's law here? Now I'll explain that. See, we have to define the Ohm's law as at a constant temperature, okay, the potential difference between the two terminals of a conductor is directly proportional to the current flowing through it. Is directly proportional to the current flowing through it. Okay, see here, how do we explain this? At a constant temperature, the potential difference between the two terminals of a conductor is directly proportional to the current flowing through it. Which means that whatever we have derived that from J is directly proportional to E in my previous lecture in 3, current electricity 3, there we have derived from J is directly proportional to E. From this, finally we have derived that delta V is directly proportional to I. This is what the definition, or this is what the statement of Ohm's law actually. Okay, delta V, it's not potential, it is potential difference. Potential difference is directly proportional to current. Okay. Now, it means that, for example, if we consider a wire simply, if we take a wire, okay, if there is a potential difference, if there exists a potential difference between these two terminals of a wire, okay, let us consider the potential at point A is VA and the potential at point B is VB. Okay, then what is the potential difference that exists here? It will be VA minus VB. VA minus VB. That is VA minus VB. That is nothing but potential difference. And that will be directly proportional to the current flowing through it. That will be directly proportional to the current flowing through it. Assume that suppose if VA minus VB, which means that if delta V is 3 volts, okay, delta V potential difference is 3 volts, we are connecting simply that wire to a battery. That potential difference which is being provided to the wire, let us assume it has 3 volts. Generally battery, what is that potential difference which can be produced by a single battery? That is 1.5 volts. If we connect 2 batteries, then we will get 3 volts. Am I right? Like that, if we connect those 3 volts to this wire, to the 2 ends of the wire, then what happens? Some current flows through it. If we go on changing that, potential difference with the help of 3 batteries or with the help of 4 batteries, means we are changing the potential difference. Okay, we are changing the potential difference. If it is 3 volts, then current will be different. If it is 4 volts, the current will be different. If it is 5 volts, the current will be different. Like that, means the current will be increasing continuously. If the potential difference increases, then the current will also increase. You can understand this in a simple way. How? Suppose if an arrow is connected to a bow. Okay, if an arrow is connected to a bow. Okay, now what we are doing, assume that the arrow is an electron. Assume that an arrow is an electron. The arrow is an electron. Now it is connected to bow like this, and what we are doing, we are pulling that. If we pull that to some extent, okay, now then it gains certain energy. That energy we call it as potential energy, right? Still, if we pull it, it gains still more energy. Still, if we pull it, it gains still more energy. If we release it, then that potential energy gets converted into kinetic energy. Even here also the same thing we are applying. We can imagine like that. If we are giving 1.5 volt to 1.5 volt potential difference to an electron, then it goes with some kinetic energy or some velocity. Okay, now based on velocity only, the current will be produced. What velocity? Drift velocity. Yes or no? Right? So if we give still more potential difference to it, now if we increase it to 4 volts, then what happens? Then again its kinetic energy increases. The electron's kinetic energy increases. It goes with a greater drift velocity. That's why current will be increased. Do you understand? Then again, if we increase that still more, means we are giving energy to the electron. If we are providing the potential difference, between the terminals of the conductor, it means that we are providing the energy. We are providing the energy to the electron. Do you understand? So whatever the energy we are providing to the electron, then automatically that electron will move with that much of drift velocity. Then opposite to that of that drift velocity of electron, we used to take the direction of current. If drift velocity increases, current also increases. From where does the drift velocity increase? In the previous class, if you observe, if you follow my previous class, from where does the drift velocity increase? From electric field, which is inside the conductor, which is set inside the conductor. From where does that electric field produce? From potential difference which we are giving to the 2 ends of the wire. That's the thing which happens here. Understand? So that delta V is nothing but which is you have to keep in mind that the energy which is given to the electron. If delta V is increasing, you are giving more energy to the electron. Understand? As soon as it is released, then what happens? It will go with, or it constitutes the electric current. It constitutes the electric current. Am I right or not? So therefore we can write it as delta V is equal to, there should be some constant, right? That constant is R. So it is R times to that of I here. It is R times to that of I. What is this R? See, whatever the energy we are using, we are giving to the electron. The total energy cannot be converted into the total potential difference cannot be converted into I. No? Somehow there will be loss. Yes, sir. So that is because of some resistance. Am I right or not? That is because of some resistance, right? So that here this R is nothing but the resistance. This R is nothing but the resistance. Okay. So here R is a proportionality constant we are writing here, and further we can understand that this R is nothing but resistance of a conductor. Okay, resistance of the conductor. See here, what is this resistance? In the beginning of Ohm's law, I have already explained that at constant temperature. Why we have to say like that? At constant temperature. Okay. See, at constant, suppose if we go on giving the potential difference to, if we go on increasing the potential difference, okay, to the two ends of the wire, then after some time, definitely there will be a temperature difference in the wire. Okay, that temperature difference is because of the resistance which is offered by the wire, which is offered by the conductor. Okay, that's why we have to say at constant temperature. Only at constant temperature Ohm's law is applicable. If the temperature is not constant, then Ohm's law is not applicable. Understand? So therefore, R here we are writing it as resistance. Then how can we understand the resistance here? Resistance can be defined as resistance of a conductor. It is denoted with the letter R, and it can be defined as the property of any conductor that opposes the flow of electrons. That opposes the flow of electrons is called resistance. See here, resistance is a property of conductor. Okay, how can we understand that property? For example, let us consider a simple example of resistance. Okay, suppose in a room, in a classroom, there are, or in a small room, there are 30 members. Okay, 30 members are staying in a room. Now suddenly what happens? Suddenly, if all of them have to rush out of that, okay, if all the people have to rush out of the room, only one door is there. Okay, one door is there, right? At a time, how many members can pass through the door? At a time, how many members can pass through the door? Maximum 2 people, not more than that, right? Then what does it mean? It means that it is allowing 2 people. It is allowing 2 people through the wire. Okay, now it is allowing 2 people through the door at that instant, and at the same instant, okay, it also means that it is opposing the remaining 28 members. It opposes the remaining 28 members. Am I right or not? Why? Because those 28 members cannot go at a time. Okay, those 30 members cannot go at a time. That's why any conductor has a certain property which can allow the flow of electrons to pass through it and which can oppose the flow of electrons. Yes or no? In a queue also it will be the same scenario, right? There is a queue line. Okay, now there is a police. Okay, he allows only one or two people, and at the same time he opposes the remaining people. When he allows two people, it means that is called as conductance. Okay, and when he is opposing the other people, it means that he is opposing the flow of people, right? Even here also the same thing is there. Any conductor allows the flow of electrons, that is called as conductance, and that property or that phenomena is called as conductance, and at the same time it opposes the remaining electrons. That phenomena is called as resistance. Okay, so this is called resistance, and that resistance, now we can also write this on what factors does it depend upon. On what factors does it depend upon? See here, resistance of a conductor depends upon, see it is denoted with the letter R, and SI unit of this resistance, SI unit of resistance is ohm. SI unit of resistance is ohm. Okay, and it depends upon some factors. What are those dependent factors? Here resistance depends upon length of the wire or length of any conductor. What happens if length of the conductor increases? Suppose if there is a small queue line. Okay, if you want to go through a small queue line, it will be very easy. Whereas if there is a long queue, then it will be somewhat tough to go through it, am I right? Because the length of the queue is very long. So obviously if length increases, what happens to its opposition? What happens to its resistance? It also increases. Am I right or not? Therefore, R is directly proportional to L. And also resistance is inversely proportional to A. A means what here? Here A means area of cross section. Area of cross section. What is area of cross section here? See here, if we consider a wire, if we take a wire, I'm sorry. We take a wire like this. Okay, now let us assume that this is a wire. Here, if we go through it carefully, it will be it has a particular cross-sectional area. It is in the form of a cylinder. It is in cylindrical shape. It has a particular cross-sectional area, right? So that cross-sectional area, we are writing it as here A. The cross-sectional area of this wire is A. What happens if cross-sectional area increases? It means that it's a thick wire. If cross-sectional area increases, what does it mean? It means that it is a thick wire. If cross-sectional area is very less, then it means that a thin wire. Okay. If we take a thick wire, what happens to the flow of current? Flow of current is more. Why? Because electrons will go very easily. Means opposition will be less. Means resistance will be less. Electron can go very easily. Why? Because cross section is more. Therefore, R is inversely proportional to A, and R is directly proportional to, combiningly we can write it as L by A. Therefore, R is equal to rho L by A. What is rho here? Again, there is a term called rho here again. This is a new term. What is rho here? This is nothing but specific resistivity. Specific resistivity. What is a term called specific resistivity? How do we explain that? Specific resistivity means it can be written as Ra by L. See, any conductor you may take, any wire you may take, okay, for unit length and per unit cross-sectional area. If you take that unit length of a conductor and unit cross-sectional area of any conductor, how much resistance it offers? It depends upon nature of the material. Am I right or not? Same length, same cross-section area. Okay. We are taking 4 different wires of same length and same cross-section area. 4 different wires. One wire is made up of copper, one wire is made up of silver, one wire is made up of aluminum, another wire is made up of gold, something like that. 4 wires are of same length and same cross-sectional area. So dimensions are same. The wires dimensions are same, right? Length is same, area cross-section is same, thickness is same. Then each wire will give a different value of current. Suppose if we connect those wires to the same battery, then if we keep the terminals of the battery, if we keep the terminals of wire, okay, which wire? Copper wire to a battery, it will give one current. Okay, if we remove that copper wire and if we just add silver wire in between the 2 terminals of the battery, then current will be different. If we take a gold wire, then current will be different. Why is it coming? Why? Because though the length and area cross section are same, it is depending upon the nature of the material. It is depending upon the nature of the material. See, nature of the material again, why? Why nature of material? According to nature of material, why does it change? Why? Because in the beginning, I already told you that the drift velocity depends upon the density of electrons. Density of electrons. Am I right or not? Drift velocity depends upon the density of electrons. Current depends upon the density of electrons. Means N, electron density. Okay. So electron density means if we take a unit volume of any wire, okay, the number of electrons will be different for each metal. The number of electrons will be different for each metal. So that's why N will be different for different metals or materials. That is why. So if there is a more number of electrons are there, obviously current will be more, no? If less number of electrons are there, current will be less automatically. Yes, sir. So that is the thing which is happening here. So depends upon the nature of the material. One more phenomenon or one more physical quantity can be defined, that is specific resistivity, and it is defined as the resistance offered by, and it is defined as the resistance offered by unit length and unit cross-sectional area. Unit length and unit cross-sectional area. Do you understand? Right? And the SI unit of specific resistivity, SI unit of rho is, how can we say? R means ohm, no? Into meter square. Area of cross section is meter square by length is meter. Meter square gets cancelled. And what is a unit? Ohm meter. That is ohm meter. Right? That is about specific resistivity. Okay. So there are some conductors. There are some conductors which obey Ohm's law. Those conductors are called as ohmic conductors. For those ohmic conductors, see here, if you plot a graph for ohmic conductors, just a minute. See here, if you plot a graph between and V and I, potential difference and current. So plot a graph between V and I by taking V on x-axis and current on y-axis. Current on y-axis. Vi. Okay. Then for ohmic conductors means what? They obey Ohm's law. Okay, up to a particular value of potential difference, then we used to get a straight line in that graph. We used to get a straight line in that graph. See here, that will be like this. Oh, sorry. Assume that it is going exactly, it is passing through origin. Why is it passing through origin? How can you say that? That is, here V is equal to I into R. Am I right or not? This equation is, this formula is similar to that of Y is equal to mx, which is nothing but the equation of a straight line here, which is nothing but the equation of a straight line. Okay, and if there is no C here, actually the equation of a straight line is Y is equal to mx plus C. Okay, if there is no C, if C is equal to 0, it means that the graph is, the line, the straight line is passing through the origin. Understand? So that's why we are calling it as, if we get a straight line, then we call it as ohmic conductor. Even this is also possible only up to certain level. Okay, more than that, if we give potential difference to it, if we go on increasing that potential difference, then what happens, then it does not obey Ohm's law even after some time. Even you can take ohmic conductors after some time or after getting heated up, then it does not obey Ohm's law. So only up to a particular value of potential difference you will get the current relation as a linear relationship. We call it as linear relationship. Okay, na? Up to there only it is linear relationship. Otherwise, after that, then it does not follow a linear relationship. There are certain other materials, okay, other conductors which are called non-ohmic conductors. Let us consider semiconductors. These are non-ohmic conductors. These do not obey Ohm's law. And the gaseous conductors, those also do not obey Ohm's law here. Okay, let us discuss. If we can go through that, then you can understand that very easily. When we discuss about semiconductors, there we will discuss it in detail. Okay, but until then, you just keep concentrating on this one. Ohmic conductors means in this. See, what is the slope of this? What is the slope of this curve? The slope of this curve, or the slope of this straight line, m, it is equal to resistance. Slope of this line refers to resistance, which means that suppose if we draw one more line, like this. We draw one more line like this. Okay, then consider that this is A, line A, and this is B. In these two, these are graphs drawn to different materials. Okay, now A is one material, and we have drawn VI graph for that A, and B is another material. We have drawn another graph for B. In this, we have got A and B like that. Okay, now the straight lines of A and B like that. In these two, which one has more resistance? Just by looking at the graph, we have to say, if you want to say by looking at the graph, then which one will have more resistance? The straight line for which the slope is more, then it will have more resistance. Am I right? So is the slope greater for A or B? It is for B. Why? Because slope formula is y by x. Am I right? Slope formula, if it is a straight line, then we can write it as y by x. So y by x value, if we can take that, then for B, the y value is more. and the x value is less, then obviously what happens? Obviously y by x value is more for B. That's why the resistance is more for B here. Resistance is more for B. Understand? Why? Because we have to consider the slope of the curve or slope of the straight line. Understand? So this is about resistance. Now let us discuss about what is the difference between EMF and potential difference. What is the distance between EMF and potential difference? EMF and potential difference. See, what is the difference between the EMF and potential difference? See, EMF will be generated actually by a battery. Yes or no? So inside the battery, what happens? EMF is produced by a battery actually. Okay. And in that battery, some chemical will be there, right? In that battery, some chemical will be there. See here, let us take this is a battery. And in this, there are two terminals. This is one terminal and this is the another terminal. Let us consider this is positive terminal and this is negative terminal. Okay. Now, in this, if this is a positive terminal of the battery, inside that some chemical, these two are two plates here. These two are two plates. Okay. See, this is positive terminal and this is negative terminal. Okay, there are two plates in it. One is positive plate and the other one is negative plate in this battery. Now you know what? In that chemical, there exists one force first. There develops one force will be developed due to that chemical. That is called as chemical force. You know what? What is the duty of a chemical force? Okay, that chemical force actually takes the positive charges, takes all the positive charges towards the positive plate and negative charges towards the negative plate. Okay, suppose there is a charge Q, there is a charge Q, positive charge, and on that some force will be applied and that is being taken to the positive plate. Okay, now. So on the positive plate, there is an accumulation of positive charges because of the force applied by chemical. That is called as chemical force. Okay, that is called as chemical force. Okay, now. So this chemical force develops and it acts on positive charge. Okay, and it moves that positive charge towards the positive plate. Meanwhile, you know what happens? One more, due to the electric field which is set inside that chemical, inside that battery, one electric field will be set in the opposite direction, and that electric field will take the charges from positive plate to negative plate. This is called as electric force. This is called as electric force. Both will occur at the same time. Got my point? What happens here? The electric field is set inside the battery and that electric field exerts a certain force on that charges and it will move from positive to negative charge. And at the same time, chemical force moves that positive charges towards the positive plate. Both will occur at the same instant of time. After some time, you know what happens? After some time, everything gets equal. Like chemical force is equal to electric force. Chemical force is equal to electric force here. Got my point? So after some time, both will get equal. Both are getting equal here. Chemical force is equal to electric force after some time. Then whenever that chemical force is equal to electric force, then we can say that the battery is being charged. The battery is being charged, and we just call it as a full battery. I mean, perfect battery now. Okay. Now there is a work done by the battery. There is a work done by the battery. Yes or no? What is that work done? Means work done is generally written as work done is generally work done by the battery. Means what? Battery inside the battery chemical will be there, no? So work done by chemical force. Okay, na? Whatever the work done by the battery we are discussing, it means that we are discussing about work done by the chemical force. So which is that is work done by chemical force. Chemical force. That is W is equal to Fc into, let us assume that both are separated, both the plates are separated by distance d, let us assume, then Fc into d by, okay, this is work done. So that work done per unit charge, if we consider, this is actually the work done by chemical force, okay, to move it in between the two terminals, to move a particular charge in between the two terminals. Okay. So from where to where it is bringing that charge. It is bringing this charge from one end to other end, means to a distance d. Yes or no? So therefore, work done by that chemical force can be written as Fc into d. Therefore, work done per unit charge is written as potential. Is written as potential. Yes or no? Work done per unit charge is called or potential difference. Okay, work done per unit charge is called as that potential difference. That work done per unit charge, and that work done per unit charge. Okay, na? Which work done it is? It is work done by chemical force. So work done by chemical force per unit charge is called as electromotive force. Electromotive force, e.m.f. In the name, it is actually force. It is mentioned as force, but it is not the force. It's nothing with the voltage only. It's nothing with the potential difference only. Understand? So it is e.m.f, electromotive force. Okay, now, as a name, it is mentioned as force, but it is not the force. It is potential difference only. It's nothing but voltage only. But it is voltage, or it is a work done by chemical force. It is a work done by chemical force. Do you understand? Now, if we connect the two terminals of this battery to a wire, see, these are two terminals. Let us consider this terminal and this terminal. Okay, now if we connect these two terminals to any wire like this, if we connect the two terminals to any wire, okay, then you know what happens. Inside the battery, it is not inside the battery, it is external, right? So inside the battery, chemical force will act, and outside of the battery, what will be acting here? Electric force will be applied. Why electric force? Why? Because due to the, I already explained in the beginning, inside the wire, electric field is set. Am I right or not? So if the electric field is set, what is the force of which is produced by electric field? Fe, electric field, Fe is equal to, sorry, electric force Fe is equal to capital E into Q. Am I right or not? This is explained in, okay, electrostatics. Okay. that when that electric field is developed, automatically electric force will be acting on it, and due to that electric force, okay, the electrons will be, or a positive charge. If we take that inside the battery, okay, na, a positive charge Q is being taken from positive terminal to the negative terminal here, positive terminal to negative terminal, whatever it may be. So if we consider inside that battery, then work done by electric force per unit charge, can be written as potential difference. It is as simple as that, potential difference. Work done by electric force is explained as potential difference. Work done by chemical force is explained as e.m.f. See, when this wire is not connected to any, I'm sorry, this battery is not connected to any wire like this. Simply the two ends of that wire are left free. They are not connected to any wire. Okay, na? The two ends of the battery are left free. Then what does it mean? It means that the current does not flow through it. When that current does not flow through it, then automatically we can say that here, in this situation, when it is open circuited, we can say that as open circuited means current doesn't flow. When this is open circuited, then we can say that EMF is equal to potential difference when the circuit is open. When the circuit is open, means when there is no current, then automatically EMF is equal to potential difference. Or just for a new battery, EMF and potential difference both are same at the two terminals. Why? Because it is not yet connected to any wire, right? Whenever it is connected to any wire, then obviously automatically potential difference and EMF both change. Potential difference and EMF both change definitely. Okay, now how does it change? How does the potential difference and EMF change? Let us discuss. Right? So if we consider now, this is a battery. It's a battery symbol, right? It is a battery symbol. Okay. Now, this is a symbol of resistance. Assume that the EMF of the battery is E and the resistance it is R here. Understand? The resistance is R here. Now, when a wire is like this, okay, at the two ends of this wire, let us take this end as A and this end as B. Okay, if we consider this situation, assume that the resistance is R. Okay, then here EMF, the question is that is EMF E equal to delta V across AB? Delta V across AB, or delta V across AB means let us simply write it as VAB. Simply let us write it as VAB, means VA minus VB, delta V, potential difference. In this situation, is E equal to VAB? No. Suppose when current is flowing through it, and that's what I'm saying, when current is flowing through it especially. Suppose if the current is flowing through it in this direction, in this wire, in that total wire, the current is flowing like that. Then we can say that potential difference is not equal to that of okay, now EMF of the battery. Let us consider the EMF of the battery is, say it is 9 volts. Assume that the potential difference, EMF of the battery is 9 volt. 9 volt battery is there, and also the resistance of it is, assume that it is 2 ohm resistance, and the current is flowing like this. Assume that the current is 1 ampere. Current is 1 ampere. Let us take that at point A, the potential is VA, and at point B, the potential is VB. We need to find out the potential difference between A and B. Okay. Is it 9 volts? Definitely not. Okay. Let us consider how is it correct. Let us discuss now. So at point A, the potential is VA. Now, when when the electron is passing from A to B, when the electron is passing from A to B, then what happens while the electron is passing from A to the positive terminal of the battery, then from the positive to the negative terminal of the battery, it moves. Then what happens? There is a drop in the potential difference. There is a drop in the voltage. Why? Because from negative to positive, what happens? It means that we are giving the energy. From positive to negative, we are losing the energy. I mean, the electron is losing the energy. That's why the potential at A is VA. After that, when it passes through the battery, then it loses 9 volt automatically. It loses 9 volts. Okay, minus. Okay, na? The current will be opposite to the flow of electron here. Am I right or not? That's why we can say that. Here. Let us consider. The current is opposite. No, that's why we have to say minus. When the current is opposite to the direction of flow, what we are going, then it will be taken as minus. If the current is also along the same direction as we are moving, okay, now, then it can be taken as negative only. No, then it can be taken as positive. But here it is negative. Why? Because it is coming opposite. Current is coming opposite. We are going from A to B, but the current is from B to A. See here in this total, from B to A. Am I right or not? Therefore, here the current is 1, and what is a potential drop across this resistor? We can say that 1 into 2. V is equal to IR. According to Ohm's law, V is equal to IR. Therefore, it can be written as V is equal to IR. That's why I is 1 ampere and R is 2 ohms. So 1 into 2, it is 2. Okay. And minus VB is equal to 0. Or else all of them is equal to VB. Okay, now anything you can take. This is the thing which we have to consider from A to B. This is how we have to write that equation, right? Therefore, VA minus VB, okay, minus 9 plus 2 is equal to 0. Therefore, we can write it as VA minus VB is equal to, it is minus 9 plus 2 is minus 7. When it goes to that side, then it will become 7 volts. So potential difference between them is actually 7 volts, whereas EMF is 9 volts. Means what? Potential difference is lesser than EMF. It is not equal. Because of what? Because of the resistance. Because of this resistance, okay, now here the potential difference and EMF both are not same. Because of this resistance, what happens? You know what happens because of resistance? The energy of that electron is being reduced. Whatever the energy it is gained from the battery, okay, now that some part of that energy is being reduced. Some part of that energy is being reduced, and it converts into heat energy, which is equal to I square RT. We will discuss it later. Okay, that heat energy. Okay, now. So that is delta V. We have got it as 7 volts. See here what happens if it is a situation here EMF is greater than potential difference. If this is a situation, it means that current is drawn from the battery. Current is drawn from the battery. Here E is not equal to delta V. When is it equal to delta V? When I is 0. Suppose when I is 0, then automatically current is, when current is 0, then automatically E is equal to delta V only. Why? Because See here, VA minus 9 is there, and minus of minus 1 into 2, 1 is not there, 0. Let us consider I value 0. Then what happens to this total value? It is completely 0. That's why VA minus VB is equal to, again, you will get 9. So EMF is equal to potential difference. In what situation? When there is no current. When there is no current. Understand? Suppose the same situation if we discuss it in a different way. Now let us assume that it is a terminal A. This is a battery. And this is a resistor. And this is B. Okay. Let us take this as VA. Potential at point B is VB. And this is same 9 volts. And this is R resistance is 2 ohm. 2 ohm resistance. But the current direction is opposite. Means opposite to the previous example. And that value is same thing, that is 1 ampere. Then what, how we have to write here? VA minus 9 minus 1 into 2. Here previously we have not taken just plus, we have taken minus 1 into 2. Here we are taking plus 1 into 2. Minus VB is equal to 0. Therefore, VA minus VB minus 9 minus 2 minus 11 is equal to 0. That is delta V is equal to 11 volts. Here E is greater than, E is lesser than, here E is lesser than delta V. Yes or no? In this situation, we can say that current is flowing into the battery, which means that, you know, current is flowing into the battery, which means this is called as charging of a battery. In this situation, it is charging of a battery, and in the previous situation, it is called discharging of a battery, which means that current is drawn from the battery. When can we say that a certain current is drawn from the battery? Here, in such situation, we can say like e.m.f and delta V both are not same. If both are not same, then we can say that some current is flowing through it. Either some current is utilized by it or some current is flowing through it. Understand? These are the two different situations. You know, whatever the battery we may consider, initially when we take it from outside, the voltage of the battery is given as 1.5 volts. But when we connect the two terminals of that battery to a multimeter, digital multimeter, where it can measure the voltage of any electrical component. Okay. So if we can measure that voltage of a battery, then it does not give you 1.5. It will give you less than 1.5. Suppose if it gives 1.4 only, you know what is happening inside that? Inside that, if we connect to it, it is not a perfect battery. Okay. Now, suppose if we take 1.5 volt battery, then if it is showing 1.4 only, if it is showing you, if you measure that voltage, if it is showing 1.4 only, it means that it is not a perfect battery. There is some internal resistance in the battery. That's why, what is that internal resistance causes? What does it cause? That internal resistance of the battery causes the heating effect inside the battery. The heating effect inside the battery means that internal energy inside the battery, the internal resistance inside the battery causes thermal energy inside the battery. Means it is wasted in the form of thermal energy. It is wasted in the form of thermal energy. That's why we are getting less value. Okay. So that's why ideal battery means it is a perfect battery for which there is no internal resistance. If it is not an ideal battery, and definitely it will have an internal resistance. In the next class, I will tell you what is the internal resistance of the battery perfectly, and I will tell you Kirchhoff's laws in the next class. Thank you all. Keep watching my channel. Keep watching my videos. Definitely keep informative, and you can gain the knowledge, conceptual knowledge. Okay. Thank you, everybody.